Hey everyone, and welcome back to The Explainer. Today, we are putting on our detective hats and diving into some 8th grade geometry. We're going to treat math like a grand investigation, where we uncover the hidden rules of trigonometry. Because honestly, if you've ever looked at a complex math equation and thought it looked like some kind of secret code, you are exactly right. And today, we're going to crack that code together.
Okay, let's dive into this. Here is our map for today's mathematical investigation. First up, the unit circle basics, then the Pythagorean identity, complementary cofunctions, verifying equivalent expressions, a quick explainer recap, and we'll wrap things up with a final transfer question.
All right, part 1, the unit circle basics, setting the scene. So, every good detective needs to know the layout of the crime scene, right? And for us, that scene is the coordinate plane. We need to establish the fundamental rules of the mathematical space we're working in, because this concept acts as the anchor for absolutely everything else we're going to do today. The unit circle is simply a circle centered right at the origin, 0, 0, with a radius of exactly 1. When we draw an angle, which we'll just call t, from the center, it hits the circle at a specific point. That point has an x and y coordinate. Here is the golden rule, you guys. The cosine of that angle is the x-coordinate, and the sine of that angle is the y-coordinate. Cosine is x, sine is y. Literally burn that into your memory.
All right, let's do a quick pause check to test your recall on those coordinate rules we just set up. Here's your question. If an angle is in the second quadrant, so that's the top left section of your graph, what is the sign of its cosine? Is it positive or negative? Take a second to really think about the x and y coordinates in that specific quadrant.
Got your answer? Well, in the second quadrant, you have to move left from the origin, meaning the x-coordinate is negative, and since we just learned that cosine is always the x-coordinate on the unit circle, the cosine of any angle in the second quadrant must be negative. It's actually so deeply satisfying how the physical geometry of the unit circle directly dictates the sign of the trigonometric function.
Moving on to section 2, the Pythagorean identity, a powerful tool.
With our foundation firmly set, we are ready to gather the heavy-duty tools we'll need later on to verify some seriously complex equations. On the left side, you'll see the classic Pythagorean theorem applied directly to our unit circle. Because the radius is 1, a right triangle drawn inside that circle has legs of length x and y and a hypotenuse of 1. So, x squared plus y squared equals 1 squared, which is just 1. But wait, remember our golden rule? X is cosine and y is sine. And this brilliantly illustrates how substituting our x and y definitions directly transforms a classic geometry theorem into our first massive trigonometric identity on the right. Cosine squared t plus sine squared t equals 1.
All right, section 3, complementary cofunctions, complementary angles.
So that's our second major clue secured. Let's look at our third and final tool for this investigation. Right triangles are kind of sneaky. They hold these hidden symmetrical relationships just waiting to be uncovered. Think about the two non-right angles in a right triangle. Since all the angles in a triangle must add up to 180 degrees, and the right angle obviously takes up 90, those two acute angles must add up to 90 degrees, or in radians, pi over 2. They are complementary. Because of this exact geometry, the side opposite to one angle is the exact same side adjacent to the other. Notice in our table, this means the sine of an angle t is the exact same ratio as the cosine of its complement, pi over 2 minus t, and vice versa. Sine of t equals cosine of pi over 2 minus t.
Time for pause check number 2. We need to make sure you fully grasp this cofunction relationship before we put it to the ultimate test. So, here's the question. If the sine of angle t is 5 over 12, what is the exact value of the cosine of pi over 2 minus t?
If you said 5 over 12, you absolutely nailed it. By the cofunction identity we just uncovered, those two expressions are completely equivalent. If the sine of an angle is 5 over 12, the cosine of its complement is also exactly 5 over 12. I gotta say, your mathematical detective skills are getting really sharp. Let's keep this momentum going into section 4, verifying equivalent expressions, step by step.
Now it's the moment of truth. We've gathered all our clues and tools. It's time to solve the case by taking a complex equation and proving that it's true step by step. So the crucial point is our golden rule for verifying trigonometric expressions. We only ever manipulate one side of the equation. We never ever assume the conclusion is already true by moving things across an equal sign. We are trying to prove that the messy expression on the left equals sine t. Look at step 1. We start strictly with the left side, 1 minus cosine squared t, all divided by cosine of pi over 2 minus t. Now let's use our detective tools. In step 2, we recognize a variation of the Pythagorean identity. If sine squared plus cosine squared is 1, then 1 minus cosine squared is exactly sine squared. So our numerator becomes sine squared t. Now for step 3, let's look at the denominator. Cosine of pi over 2 minus t, hey, that's our cofunction. That is exactly equal to sine t. Finally, step 4. Our fraction is now sine squared t divided by sine t. One of those signs cancels out, and we are left with precisely sine t. Case closed. We logically verified the expression without ever crossing the equal sign.
Section 5. Explain or recap. Reviewing the clues. Honestly, that was incredibly satisfying. Let's just lock in the foundational rules we've uncovered today. Look at how far we've come from basic right triangles to working with abstract identities. First, we anchored ourselves in the unit circle, learning that the x-coordinate is cosine and the y-coordinate is sine. Second, we leveraged that geometry into the Pythagorean identity, discovering that cosine squared plus sine squared equals 1. Third, we explored cofunctions, proving that the sine of an angle equals the cosine of its complement. And finally, verification. We learned to use these identities as tools to manipulate just one side of a complex expression to prove equivalence.
And finally, Section 6, Final Transfer Question. Solve the case.
Now, it wouldn't be a proper detective training without leaving you with a cold case of your own to solve, would it? I am officially handing the magnifying glass over to you. Here is your final mystery. How would you use the Pythagorean identity and cofunctions to verify that sine squared of pi over 2 minus t plus sine squared t equals exactly 1? Look really closely at that first term. You know exactly what happens when you have a trig function acting on pi over 2 minus t. You now possess all the logical tools you need to crack this new case completely on your own. Good luck, detectives, and keep exploring the amazing patterns hiding inside the math. See you next time.